Thank you.
Carlo Rovelli, you will talk about multiple observers.
Thank you. Well, first, thank you, all of you, for being here. Thank you, Fabio and the group here for the hospitality. Actually, I want to say thank you in particular to Destiny for the organization. And she's not here, to Christine, who is our project manager in Marseille. But most of all, let me start by expressing my huge gratitude to Marius, because he's really the sole scientific and organizational of this, all this. And I think it's wonderful what Marius has done bringing this together. We'll have more opportunities to thank him, but I think it's good to start recognizing his role in that. I have the heavy task of starting, and I decided, first I thought, well, let me give my general view of quantum gravity and how do you do measurement in quantum gravity and all that, and talk about loop quantum gravity and how we do that in the sort of loop quantum gravity community. But then I thought that's not a good idea, because the point here is that we get together, we try to open a space of discussion between us and between the different ways in which we have in which we approach similar problems. So I decided to do something completely different, and to give you a set of consideration of thoughts about what I hear many of people in the collaboration are doing, and in particular the possibility of thinking of multiple observers localized in different space-time region, observers in the sense of quantum mechanic observers. What I'm doing here, it's basically a reaction to some of the things I read in papers of various people sitting in the audience here, even more talking directly to them, and even more talking directly to the students and postdocs of them, which is the best way of getting information about what's going on in the community. I'm not sure if what I'm going to say is completely obvious to all of you, so I'm going to say trivialities, or whether it clashes strongly against some of the things you do. I hope it's something in between, not because I want to teach anything, but I want to open a discussion of a number of things. I think we have some sort of different assumptions, and it's good when we compare them and we discuss on them. So I'm open to, not sure of everything I'm saying. I'm saying all this to start this way, yeah. These are the topics which I will address. So the causal structure between different observers, and to discuss that, first, what is time orientation in quantum mechanics, how it comes in, and then, which is perhaps the most important thing here, the compatibility, I'll say exactly what I mean, between different observers. I think these are themes that if we want to do quantum mechanics of space-time, if we want to do general relativistic quantum mechanics, we have to address and to discuss deeply, not to go in the wrong direction. Now, let me start. This is preliminary to go into the discussion. Let me start by a general consideration on quantum mechanics. We all, not just in the community, but as theoretical physics in general, think about quantum mechanics in very different manners, which are ultimately compatible, but are remarkably different. And in fact, I live moving between different communities, and quantum mechanics seems a very different beast between different communities. And roughly, one way of dividing the views of quantum mechanics is this one, among the various differences. There are some people who think about quantum mechanics in terms of the reality of the quantum state and the wave function. Think about the many world people, the philosophers in Oxford, for instance, think about some cosmologists and so on. So quantum mechanics is about a psi that evolves as a Schrödinger equation, the Witt equation, and the rest should come out somehow out of that. And then there is a completely different way of viewing quantum mechanics, which is far more popular among people, many of the people in this room, which is to view psi epistemically rather than realistically, which doesn't mean not to be a realist, it means to look psi, interpret psi not realistic, and to focus on the, take an operational point of view, even an instrumentalist point of view, take say quantum mechanics about still things that we measure, we observe, the numbers we see in the laboratories, quantum mechanics about facts. This is black, this is here, and we compute probabilities of seeing something, giving something else. And this is the other perspective about quantum mechanics. These are not necessarily incompatible, philosophically different, right? But it's not physically different in a sense. And let me be clear, my sympathy is definitely here and not there, by far. The perspective of interpretation of quantum mechanics, which I like, the main one is the relational quantum mechanics, which is in this work, definitely not in this work. I think that taking psi realistically is a mistake, which leads to wrong intuition and wrong consequences. I think that psi has to be interpreted epistemically. Nevertheless, I think all points of view are good, like always in physics. The more ways you have to think about the same physical phenomenon is fine, right? The better you understand it. And especially, all my sympathies are here, but careful, because when the observers are multiple, there is care required in taking this perspective. That's, in a sense, the entire point of what I want to say. So the general situation I'm discussing is when you have two laboratories. This is interesting because Lucien, many people have pointed out that could be a very good starting perspective in thinking about quantum mechanics and general relativity. Of course, in general relativity, you can think about general relativity as you can think about gravity as the theory of relation between observers in a different sense, in a sort of space-time point of view, located in different part of the manifold having different inertial frames and the relation between the inertial frames. So it's definitely interesting to bring together these two different notions of observers and try to think what happened when you have quantum mechanics coming in this situation. Well, that's the kind of situation I'm discussing, and I want to discuss two questions about this situation, which are crucial. One is, what about the time ordering and time orientation between these? Because if you have a single observer in quantum mechanics, of course, we can compute the probability of A given B and B given C, and we know that orders matter. Time ordering matters. So what about if the time ordering is not unique? And of course, for general relativity, in fact, for special relativity, we know that there's a partial ordering between space-time events, not a total ordering. So this opened a can of worms. And the second one, what about the quantum compatibility about the observers, which I'll get to. So but let me start from the first one. So time order. Now time order is who comes first. And who comes first has to do with the difference between the past and the future. Okay? And let me start by discussing that. Time reversal invariance in physics. And we know very well that classical mechanics is time reversal invariant in a very specific and clear sense. I think we all know that. Field theory is time reversal invariant, general relativity is time reversal invariance. All the basic theories we have to describe the worlds are time or precisely time parity or CPT, reversal invariant. What about quantum mechanics? Well, at first side, then you see immediately that here questions start coming out. If you are a realist about psi, then you say, of course, quantum mechanics time reversal invariant. The Schrödinger equation is time reversal invariant in the appropriate sense. The Wheeler-DeWitt equation is that it doesn't pick up a preferred time direction. But if you're an instrumentalist, it seems something funny is happening because measurement is not time reversal invariant. And so you cannot undo a measurement in a trivial way. So what's going on? Let me backstep a moment and go back to classical theory. Of course, classical mechanics time reversal invariant, but our experience is not. The future is very different from the past. So where is the catch? Well, we all know where is the catch there. Mechanical phenomena by themselves do not distinguish the past from the future. Thermal phenomena do. But how is it possible that thermal phenomena is a particular way of looking at mechanical phenomena? Well, the point is that what is time reversal invariant is the theory, not the individual solutions, of course. Given a solution, you can say one in a path, one path is different, one end is different from the other one. And thermal phenomena are discussions of a set of solutions which are special on one end of time, which is the one we call past. Right? This is completely clear since Boltzmann, since the discussion, since all the discussion about the origin of this breaking of time reversal invariant, the second principle of thermodynamics. So what is special is the special initial conditions. Why the universe had special initial conditions, we don't know. It's an open discussion. There are ideas. That's not what I'm discussing now. When you do thermal physics, you're not doing the full set of dynamical variables. You're doing coarse graining. Your coarse graining is such that the entropy, the number of microstates corresponding to a given set of values of your coarse grained variables is lower in one end of the time evolution by assumption. And this assumption matches very well with the world which we know. So this we understand perfectly well in the classical domain. And let me be precise, given a specific trajectory, some variable A, some variable evolving in time in the equation A of t, if I time reverse it, if this is a solution of the equation of motion, this is also a solution of the equation of motion. Okay? What about quantum mechanics operationally? Well, I want to claim that there is a specific sense in which operation of quantum mechanics, the result of measurement in quantum mechanics have a similar property, in fact have the same property. Let me argue specifically for this by using an example. Imagine you have a source of spin 1/2 particles and you do a spin measurement, say in this direction, in this direction, and you choose directions as you want. I've chosen on purpose the first two orthogonal, just for cancelling the effect of the two ends. And you make measurement, and you say the sequence of static Gabor, and you see where the particle goes. And then the spin come up has only two values, plus or minus, or 0 and 1, and you record. You say you get plus, minus, whatever. Okay? Now, from one record, you cannot say much, of course, because this is probabilistic, quantum mechanics. You can have a very unlikely outcome coming out. But if you do the experiment many, many times, you have the set of runs. The lines are the run. The columns are the end of the. From that, you have you can reconstruct the probabilities of measuring spin up and down here, given if the spin was up and down here. So there's a probability of plus here given plus here, minus here given minus plus here, and so on. So from this, you have what you have to know, all there is about the world, unless we believe in hidden variables, about the spin of the particle in a evolution. Now here's a claim. Take this set of numbers, let's say a long column, and reverse it. So define, just take it and reverse it in time. So define another set of number, which is the same going backward in time. And the claim is the following. I give you this and this, I don't tell you which is which, and I ask you which one is the physical one, which one is the real one. Okay? And the claim is that you cannot say. There's no way at all, if I didn't tell you which one was the actual measured one, to know whether the measured one was this one or this one. This is exactly the same statement that in classical theory, but transformed into probabilities, made it discrete, which is the proof is just one line, a few lines from the probability. Just compute it, and you see that the probability of going from here to here, plus minus 1, is the same as going from. So, moral, classical mechanics is time reversal invariant in the sense that given a solution of the equation of motion, the time inverted solution also is a solution of the equation of motion. Quantum mechanics is time reversal invariant in the sense that given a set of measurement outcome, the time reversal of this measurement outcome also satisfies the same probability laws. So quantum theory is as time reversal invariant as classical mechanics. Right. Well, something is fine. Because there's definitely something non-time reversal invariant in the measurement, in what we do, in how we use quantum mechanics. So where is the catch here? Well, given that, which is a fact, where does the non-time reversal invariance of the quantum measurement come from? Where is the non-time reversal invariance of the standard quantum mechanics that we study in textbooks, in which you do a projection and somehow it is forward or backward? Well, it is in two places. The first one, it's very interesting philosophically, but it's stupid. The second one is more interesting physically. So let me say what the first one is. Careful. Let's go back to the example in which I have this spin 1/2 particle at a sequence of measurement, and then a measurement here and a later measurement here. Okay? Suppose here we measure plus, and suppose here you also measure plus, just to choose one. Now question, what is the state in between? The quantum state in between? Well, if you use standard textbook says that the state, suppose the Hamiltonian is 0 there, just for simplicity. Nothing changes if the Hamiltonian was not 0. It would be a little bit more difficult to say the same thing. So suppose the Hamiltonian is 0. So standard textbook quantum mechanics tell you that the state here is determined by the previous measurement, not by the past measurement. Okay? So here, the state is plus in the basis of this spin in this direction, and not plus in the basis of this spin direction. Right? Now, why we say so? If we are operationalists, this is only because we remember that, we don't remember that. Because we, as observer, we are big, macroscopic, time-oriented things which have memories about the past and not memories about the future. So we remember that and not that. But the physics doesn't know in between here if the time direction was this one or that one. So therefore, the assignment of a quantum state to some moment in which nothing is being measured is completely conventional to what we remember and what we don't remember. Right? The physics is what I said before, is a set of outcomes. The set of outcomes doesn't distinguish the past from the future. In fact, if you reverse the argument, I believe that this is one of the strongest arguments against a realistic interpretation of the state in the ways usually given in the textbook. Because here's a proof, almost tangible, that the physics is time reversal invariance. We're adding a story which it makes sense because it talks about our memory, not about the spin system itself. we have seen these results here. We want to compute the next one on the basis of our knowledge. Our knowledge here is about that. Our knowledge here is not about that, and that's why the state is about that. Right. And this shows that the state is an epistemic, has to be interpreted epistemically and not realistically. I think that's one of the strongest arguments for an epistemic interpretation of a wave function. This is philosophy, it's not physics. The physics is time reversal invariant, as I said. All right, so let's put this one apart. Forget about this. Nevertheless, let me go to point 2. Nevertheless, there is something time reversal invariant in measurement. No doubt about this. What is it? And here comes the core of the story. So suppose we do a measurement. There is some in state, there is some laboratory, there is some out state, and in whatever happens in between, a number comes out. You can think also of something more general, if you like to, there's a standard measurement. Let me think about the measurement because I'm a sort of quantum mechanical guy. This process is not time reversal invariant, no doubt. Okay, don't go back here. So why is it oriented? Well, the best way to see why it is oriented is to look at this from a slightly different perspective. Namely, imagine that the measurement outcome, to do it concretely, there is an apparatus, a machine, or something, or somebody, which is actually interacting with that. And there is some quantum dynamics. Of course, when we do that, when we do this description, we're doing the approximation in which we are disregarding the quantum properties of the apparatus itself. So let me step back and consider the quantum properties of the apparatus itself and see what exactly is going on. Okay? And for this, the easiest thing is to look at the state. Let's look for a moment at the wave function picture, of the quantum state picture. Let's look realistically let's take the other perspective for a moment. So I have a laboratory which now is a quantum object, which has a quantum state. This is its state. And I have the system coming in, which is in some state. I start with a combined state of the two. Something happened in between, okay? And from an external perspective, what is happening is that there is an entanglement. That's what a measurement is. It's a standard analysis by Wigner. There is an entanglement between the two, so there's a certain sum over certain coefficients, and so on and so forth. Okay? That's what is actually going on. Now you see exactly what is. You start from a state, you end up in a state. The state you end up is absolutely generic for the combined system. The state you start is not generic for the combined system because it's a tensor state. In fact, if you compute the entropy as seen from sort of half the system about the other, you trace of that, you trace of that. Here you get zero entropy, here you get entropy generic is larger than zero. So in a measurement outcome, you go from a non-generic state to a generic state. The measurement itself starts from the assumption that to start with, the laboratory is not correlated with the system. So it's an assumption which is non-time reversal invariant. Aha, this is it. That's what makes measurement non-time reversal invariant. The assumption that in one direction of time, the one we call past, there was no correlation to start with the system. And you look at the correlation that you want. So time reversal invariant is broken by the assumption initial state is a tensor state, which is exactly the same sense in which time reversal invariance is broken by thermodynamics. You start from a low entropy state and then you go to a higher. You start from a special state and then you go to a higher. So all non-time reversal properties assumed in the epistemic framework are equivalent and can be derived from the assumption of an initial tensor state. Hence, they're essentially a initial low entropy assumptions. So I looked at the kind of thing that some of you guys do with various laboratories and the properties that you assume on the POVs of one special laboratory and the set of properties, and this set of properties break time reversal invariance. You sum over something, you get one in the future, you don't get one passes, stuff like that. So where does this assumption come from? It comes from that. From assuming, you want to view this as a measurement, so you want to assume this, that the quantum state of the observer, of the apparatus, was not correlated to the incoming quantum state to start. All right? Now let's come here, because all this, the point was all coming here. Having clarified this in the back of our mind, let's come here. And this is interesting because in general relativity all sorts of funny things can happen here, including general relativity allows closed time curves. So including, whoops. Including that there's a closed time-like curve that goes out of here, goes in here, and comes back here, right? You take a Gödel universe, and in a Gödel universe, there are closed time. In fact, you get a Kerr solution. In a Kerr solution, there, in an infinite, in an eternal Kerr solution, there are closed line curves. So, imagine that I take this time-oriented and this time-oriented, which is the kind of things that a lot of people think here, a setting in which a lot of people is working. Could it be that this is time-oriented and this is time-oriented in this manner? Can we have a non-trivial causal ordering about the time arrows of different laboratories? Well, the only possibility is that if you include in the picture the quantum mechanic description of this laboratory and this laboratory, then the only possibility is if the initial state here is a tensorial between the lab and the system, and also here is tensorial between the lab and the system. So the boundary state, which is all around the laboratories here, okay, must be of the form up there, whatever, and down here, this tensor this and this tensor this. So lab tensor system A, lab tensor system B. But if you want to believe that there is a dynamics that connect this with that and a dynamics that connect this with that, this quantum state must satisfy some conditions in which this is somehow connected to that and this is somehow connected to that, and this might very well contradict this. Might be incompatible with this. Or it might restrict to a very small subset of states. Okay? I believe that all conditions on the possibility of non-trivial causal structure of this kind are all expressible in the compatibility between this form and the state and the dynamics of the system. This is what is going, this is what is happening, and only this is what is happening. But careful, because think in terms of entropy. If entropy is supposed to grow from here to here, and is supposed to go from here to here, can entropy keep growing? No, because this is a closed curve. You cannot have a single function growing monotonically around a circle, obviously. So the subtle point here is that the gradient of the time, what we call the time direction, in the sense of the distinction of the past or the future, it's given by an entropy gradient. It's given by something growing. And the gradient of the entropy, which is a one form, it's a one form which is a gradient. It's a d of something. It's a closed one form. And therefore, its line integral has to be 0, right? So there cannot be a growing time, oriented time along a closed curve, time-like curves. There can be a closed time-like curves. That's the point I'm making. So in general relativity, you can have a metric where you have a line that goes around and is always time-like. But you cannot one which is always future pointing, because what distinguishes one from the other of the two possible time directions is entropy, is the d of something, and the d of something cannot grow along a closed curve. That was point 1. Now let me go to point 2, which is more 10 minutes? Okay, yeah, it's for plenty, thank you. Which is, I'll devote less time of this, but it's, in a sense, is even more crucial in my opinion. Let me go back to the situation of two laboratories and ask the following question. Let's look at this in the perspective of the EPR situation, which I'm sure you all are familiar with. I have an EPR pair with some kind of correlations, and I make a measurement here, a measurement there, and these correlations and the two measurements are correlated in a funny way. Why in a funny way? Because if you look at the details of the correlations, they violate the Bell inequalities, and the Bell inequalities are required if the correlations can be understood in terms of some hidden variables which were sort of already here, and if each one of the two half systems carried its own well-defined system. So the APR correlation cannot be ascribed to hidden variables because of Bell theorem. I mean, cannot be ascribed to local hidden variables because of Bell theorem. Of course, non-local, yes. Intuitively, the only possible alternative seems to be that there is an instantaneous transmission of information from one to the other, which is funny because we cannot use that to transmit information, and is even more hard to digest because the relativistic structure of space-time tell us that there isn't even meaning of sending information from one to the other because there's no causal correlation between the two. So how do we think about that? Well, I believe there is a solution, and the cleanest discussion is I've seen in this paper here by Pierre and Federico and myself, which is the following. The discussion is that the mistake in this that give rise to this puzzle, and this here I'm going at the core of the story, is that we're assuming that there is a measurement outcome here which we can see and a measurement outcome there which we can see instantaneously. So they both exist there for real, as seen by God. Who else? Who can see in two different places at the same time, right? So the mistake is believing in God here. If you're doing that, or you can believe in God, but you think that believing in God is relevant for that. So what's the way out? Well, let's not think in this way, and let's think operationally, critically. So suppose we want to check these correlations. To check this correlation, we have to send signals from one point to the other, of course. So suppose I'm sitting here, just to say, make an example. I'm the guy in laboratory A. I want to check the correlations. I have to wait a signal for this to get back to me. This is perfectly fine. But now I have a description from the point of view of laboratory A, where no causality is violation, no transmission of information faster than light, nothing like that. I just find some correlation between the measurement outcome here and the measurement outcome here when I measure the signal coming from there. And in the description that I give, that A gives of the world, between this time and this time, what is actually going on is the establishment of an entanglement between the laboratory and the measuring apparatus, which remain entangled, and which, in the description of A, is sort of a quantum superposition which is only resolved when there's a measurement outcome here, which is causally connected to what is happening here. So nothing funny is happening, or more precisely, nothing more funny than usual quantum mechanics is happening. Of course, it's all the being funny of quantum mechanics, which is going on, but it's a standard one. There's no transmission information at great distance. Well, but this is from the point of A. What about B? Well, what about B is just exactly the other story, because also B, to check the correlation, has to wait a signal. So from the point of view now is A, which is a quantum superposition. All right? So what does this mean? This means that this is, in my opinion, the cleanest perspective on the APR, the Bell non-locality strangeness. So Bell non-locality, of course, is there, but is not something that pertains to the actual values of measurement at space-like separations, because we shouldn't think at actual values at measurement of, because we're operational, we're instrumentalists. There's nobody checking on that. We're not doing this, the instrumentalist view of the universe from God's point of view. We're doing the instrumentalist view of the universe from our point of view. And we're either this guy or this guy, not the outside. All right. But then this means that we cannot assume that laboratory A and laboratory B can be a priori assumed to be both having well-defined measurement in general. They can in some case, but essentially they come when their various, where said it badly, the corresponding operators don't commute, or more precisely, when the measurement they're looking for decohere in the sense of the current history, in the sense of Jim Hartle and Gell-Mann, which, careful, it's a property of the operator and the state, once again, and the boundary condition. So there are some boundary conditions for which you can assign consistent probabilities to the measurement outcome of separate laboratories, but you're restricting the quantum state. And nobody in the universe tells you that the quantum state should be restricted in this manner. For a generic quantum state, you cannot assign probability to different observers because of all that, because this is quantum mechanics. You can assign probabilities to observers locally, but when you do to one, then the other one is, the probability is ill-defined. So I think we cannot assign probability to outcome of operation performed in arbitrary different space-time regions without heavy hidden assumption on their decoherence, namely on the boundary state. And this is very relevant for generativity because, and that's the point, local quantum observers, which is a fantastic idea, which I think is a correct idea to start thinking about quantum properties for gravity. So it's an idea which I deeply like, endorse, and I'm trying to learn from. But careful, they are quantum with respect to one another. You cannot assume that they're both classical in the sense that they're both the subject of instrumentalism, the subject of operationality. They cannot be assumed to define common Bell variables. Oh. Well, I'm done. I am in the time, I think, so this is my conclusion. I made 3 points. The first one is that quantum mechanics is time reversal invariant, exactly like in classical mechanics. And the time reversal is broken by special initial conditions, like classical mechanics. And in particular, the special initial conditions are assumed when you do a measurement, because you assume non-correlation between the quantum state of the system and the quantum state of the apparatus. So that's a general statement. A second, precisely because a measurement is a special interaction with a peculiar initial condition, you assume this tensor state. It determines a preferred time direction, and this is a low initial entropy condition, and entropy cannot grow on a loop. The simplest way to think about it is the two laboratories. Suppose that one does nothing. Then if one is completely trivial, then you have a loop between the income and the outcome of the same lab. So if you want the dynamics to say that the out is equal to the in, then if you assume the in is tensorial, then the out has to be tensorial, and therefore there's no measurement. So you see how strong is this. So there can be closed time-like curves, but not closed time-like curves with consistent time orientation. Along a physical closed time-like curves, entropy will have, say, a minimum and a maximum, so the direction of time is this, it's not this. And finally, multiple observable can be quantum mechanically in superposition with respect to one another, and this is a generic case. So assuming that there are two laboratories, both classical, so to say, that they can both be measurement, and that yield consistent measurement, so you can assign consistent probabilities that sum up to 1 and so on, requires that the corresponding interests decohere, which is not true for the general case, for generic boundary state that satisfy the equation of motion. Thank you. have time for questions?
Yeah, we can take a few questions, sure.
Yes, so I have one disagreement and one comment.
Yeah.
Let me start from disagreement. So, at the moment when you introduced this story, general relativity, so when you started talking about closed curves, I would say that general relativity tells us about observers, so it tells us about expectation value, about matrix elements, not about the states. So within this comment, like there will be also hidden questions. So could you still extend your story to matrix elements, to expectation value, not to the states? For instance, when you said about the argument of closed curves, so of course you can have a closed curve of a matrix element, but I would say we don't know whether we can say the same from the perspective of general relativity about the state. And then comment is that if you think about quantum general relativity, then it can be shown that in quantum general relativity, general covariance can be broken at the quantum level, and this can be demonstrated in the paper of mine that will appear on Thursday. I will submit it today. So on Friday I will continue also what you started today at your talk, on my talk. So everyone is welcome to hear it. So then because the general relativity the general covariance can be slightly deformed at the level of quantum corrections in quantum general relativity.
So let's keep it short.
Then maybe.
Let's keep it short.
Okay, I'm finishing. Then maybe it can somehow explain the problems that you found, like and you mentioned about this problem in your talk.
Well, I look forward. I just want to learn what.
So yeah, but there was this hidden question. So do you think that there will be still a problem if we will talk about matrix elements, not about states?
Yeah, I think that it's good you pose the question. Maybe it's a good program to try to re-say it in that language. But if you want the probabilities of the outcome of two laboratories to sum up to, so let's not talk about state at all.
Yeah.
To be consistent as probabilities to sum up to one, then you're restricting the possible values to cases which are not necessarily physical, which are not necessarily general. The same, I just say the same thing as before without saying state.
Mm-hmm.
What I'm saying is that there is nothing wrong in the fact that the probabilities assigned to different labs don't behave as probabilities, because they're not probabilities. They're not probabilities for anybody, only for God.
Yeah, sure. With this
But this is a open discussion. As I said, I know that some things I've said might clash to some things people say here, so I just want to open this discussion.
Thanks for the talk. I also think that compatibilities between for probability assignment in different laboratories is extremely important and not trivial, and especially in situations like Wigner's friend, when one laboratory
this is
part
it.
of the other one.
This is implicitly it, yes.
So I was thinking if you can comment on this aspect, but then comparing with the Bell's theorem, I am somehow not convinced that it's necessary. And if I understand you correctly, I'm not correct. You assume that definiteness of outcomes should not be assumed until they are collected in one single laboratory, like Alice laboratory in your example. Now, if one put this picture in mind, then a completely classical picture is also possible, and there is also Gilles Prasad, I think, has this idea that you collect that the outcomes come into reality only when Alice and Bob meet, or Bob sends a signal to Alice. And then if you wait so long, because the signals can be exchanged, you can think that it's possible to explain Bell experiment with local hidden variable. It's
No, that's not what I'm saying.
You are not, that's what you're saying, and that's what I want to kind of warn, that with the very same explanation, you can have a locally realistic explanation of it, and yours is just, you are extremely quantum, that's how I understand. so it seems to me that it's not actually necessary because these two laboratories are space-like separated, operations commute with each other. The fact that you violate that inequality is just, well, that's quantum mechanics. You don't need to, I don't think that this is an example where you have to need to collect. Because you can have, even now we don't know what's going on in Iran, but we kind of read newspapers and believe that it's going simultaneously. We don't need a gut point of view. And in Alice and Bob, you can think that Bob can, for example, they can correlate it, they can synchronize the clocks. And Bob, whenever he sees an outcome, definite outcome, says, okay, that's definite outcome, I stop my clock. Of course they have to meet to compare the clocks. But at that point, Alex can believe that he really saw a definite outcome, stop the clock when there was existence of that outcome. I don't need really to wait for this outcome. So I have to have certain level of trust in a sense, and as long as it goes, it's fine. And probably Wigner's friend situation doesn't go, and that's where we have even to modify.
Sorry
for a long time.
Yeah, I think I see what you're saying. In the Wigner friend case, you have a recent paper, right, of the Wigner friend. I was reading it in the last days. I hope we can discuss that. I think it's very interesting. It's what you do, so this time-dependent ways of viewing. But specifically to, I see what you're saying, but I believe that if you hang on to that, you're making a mistake. I think, and which are leading you to some, especially in quantum gravity, where things become increasingly complicated. Of course, you can always say, once you make a measurement, you can say, well, I can backtrack it. But you're doing the same mistake as you said. I measure the spin, and then I say, well, since the spin was like that, I believe it was like that before. You can't do that. Nobody prevents you to do that. In fact, people think about quantum mechanical reversal, back in time. But you're putting into reality something which is not into reality. This is what my intuition about that. And of course, we can say, okay, well, inequalities are there, are violated, and this is what happens, and there are no local circuits. But then you're either actually thinking that there is a non-local dynamics really going on, which is not you, or
the quantum correlations are just stronger than classical.
Right. Well, maybe we can. So my main point is that I think that if you strongly assume in general relativity, if you strongly forget in general relativity that each quantum observer is actually a quantum mechanical object seen by another observer. So if you forget the Wigner story and you don't assume it altogether, you run. That's what the main message I'm trying to make. Which might be, as you're saying, that the EPR case is not the best way to catch it out.
Okay, let's thank the speaker again.